I guess I approach science and other things in the same way, which is I really appreciate it in other people, other craftsmen, other professions um, when something is deep, not shallow. When you see that a lot of thought has been put into it and it's understated. There's no need to scream about it to the whole world because the quality and the thought that went to its construction speaks for itself.
Hello, my geeslings. It is Mother Goose, Robinson Earhart, here with the introduction to Robinson's podcast, number 56. And you're maybe wondering, maybe not, probably depends on if you're watching on YouTube, why I'm clad in a hat and jacket, and that's because I just came in from the frigid outdoors of San Francisco. When I moved here, I definitely thought it was going to be like Florida weather, which was my mistake, but apparently it's also a lot colder here than it typically is. I mean, right now I think it's snowing in Los Angeles, so go figure. But anyway, this conversation, this episode, this podcast was really great for a number of reasons. They all, of course, go back to my guest, Kevin Heng, who is chair professor of theoretical astrophysics of extrasolar planets at the Ludwig Maximilian University in Munich. And so there are a number of reasons why this episode was so awesome. One is, I mean, most of the podcasts of late have been philosophy, but I'm interested in a lot more than just philosophy. And I guess in particular, I'm quite interested in how philosophy interacts with other disciplines. So Kevin is not a philosopher. He's a theoretical astrophysicist. And he came to my attention because I saw on Twitter that he's working on, or has now completed working on, the first ever anthology of its kind on the philosophy of astrophysics, along with 3 philosophers of science, whose names I hope that I don't butcher, because with the exception of Nora Boyd, they are quite foreign names to me. So they're Nora Boyd, Vera Matarese, and Siska de Baerdemaeker. And I'll be speaking with them later on in about a month or so, and I'm really looking forward to that as well. But so they've just finished this volume on the philosophy of astrophysics, and Kevin was their sort of astrophysicist contact, and we got to talk a lot about astrophysics. Astrophysics. We talk about Kevin's work on exoplanetary atmospheres and why that's interesting, why it's important, and naturally we also talk about the search for exoplanets. And then we get into some of his work on the Anthology, for which he wrote an essay on the role of scientific models in astrophysical practice as a practicing astrophysicist. And then we also talk about some fun things like his time in culinary school and his taste in fashion. He really likes Bottega Veneta. So without any further ado, I hope you enjoy this podcast as much as I enjoyed having this conversation with Kevin. Where are you from? Are you from Singapore?
So, yeah, it's complicated. So I'm originally from Singapore, but I was trained in the US. I did my master's and PhD at Colorado. Then I did a fellowship at Princeton in this really special place called the Institute for Advanced Study. This was the place that they built around Einstein when he fled Nazi Germany. Really interesting place. It really shaped my thinking as an academic. Then I did a fellowship. Then I went to Switzerland. I did a fellowship at the ETH Zurich, the Swiss equivalent of MIT, I guess. Then I became a professor at the University of Bern, also in Switzerland. And I was tenured as a professor at Bern. I was there for about 10 years. I was also the director of a center called the Center for Space and Habitability. And the reason why this part of the story is relevant is because part of the mandate of the center was to do interdisciplinary research. And this got me in touch with the philosophers. That was my first contact with philosophers when I was essentially the the university president wanted me to stimulate interactions with philosophers and geoscientists and theologians and so on. Well, the conversation with the theologians didn't go so well, but the conversations with the philosophers started slowly, and it became more and more lively, and that led to the volume that you saw online. So to summarize, I am from Singapore. I was trained in your country, but my management experience is from Switzerland. It's a sort of an interesting mixture. Then after 10 years in Bern, I was essentially headhunted to be a professor at the University of Munich. So that's my career.
Right. Okay, great. And so were you one of those kids like me who always wanted to be an astronaut?
Yes.
Is that how you are? Yeah. Okay, that was a very quick answer. And then, so how did that transform into astrophysics, becoming an astrophysicist?
Probably the answer is similar to what you have heard before, which is after a while it became apparent that the astronaut route wasn't going to happen.
Any particular reason? Just because there are so few of them?
Well, there just wasn't a clear route, right? You at that time when you had to be some kind of test pilot, right? And I'm no pilot.
Oh yeah, like in the Air Force or something.
And that was not a profession that I could remotely see myself going into.
Okay.
So astrophysicists seem to be the next best thing. Yeah.
Got it. And then I think people have a fair idea of, maybe not, maybe I'm entirely wrong, but we have an idea of what an astronaut does on a daily basis. But I doubt many people know what an astrophysicist does on a daily basis. And since you're the first astrophysicist on the show, I'm curious about what a day in your work life looks like.
So broadly, I think it's useful to talk about the profession. So broadly speaking, I think there are three types of astrophysicists. So there are theoreticians, people who, just think blue thoughts in their head. And they are closer in pedigree to philosophers. Then you have the actual astronomers who use telescopes, and we call them observers. And you have the really talented engineers who actually design and build the telescopes, either on the ground or in space. And we call them instrument builders, right? So you have theorists, observers, and instrument builders. And I'm a theoretician. So my day looks very different from an engineer or an astronomer. So a theoretician, well, my take on it, you will get a different answer from a different theoretician. My take on it is that astrophysics theory is the business of ideas. So except it's similar to philosophy but we have rules. I'm sure philosophy has rules too, but we have different rules, right? The thoughts we think have to obey the laws of nature. We would like it if ideas we have thought about can actually be confronted or even falsified by data. That's, I think, really important. And it's important, at least the way I was taught, is important to work on ideas where there's a chance of testing these ideas sometime in your lifetime, so that the data is actually going to exist in the next decade or so. So I would say my typical day, I don't think that's a typical day. It depends on what problem I'm working on as a theoretician. But a huge part of my day is something that's not so interesting to you. I think so. That's the hat I wear as a theoretician, an individual academic. Then I wear a second hat as sort of a high-level manager. And one of the things I enjoy doing is actually enhancing the environment for the younger people I'm in charge of. And when I say that, I don't mean just students and postdocs. I mean like senior scientists and other professors. And I think it gives me joy to create this environment intellectually where I know that people can be greater than the sum of their parts.
So when you're wearing your theoretician's hat, what does that look like? Are you mainly just thinking, or are you writing in prose, or are you jotting ideas on a blackboard and working with physics equations, or talking with other or all of these things?
All of the above.
Okay.
Gosh, that's a difficult question to answer in a general sense. I would say it starts with an idea. Like it's usually driven by some phenomenon we see. Like although it's so abstract. Maybe we start with an example, right? So I study planets, exoplanets, planets outside our solar system, and one of the big questions about planets is, can you actually detect, not is there life, but can you actually robustly detect the presence of life from a distant planet, right? So if the life was there, would you be able to tell? That's the question. And so you start with questions like that, and then you think about, how's the light going to look like, right? How is it influenced by the atmosphere of the planet? Are there false positives? Are there things that are not biology that could fool you into thinking that it's biology? So you start with this kind of question. You figure out if this is something you can actually calculate. And you figure out if this is something that can be calculated in what we theoreticians call a rather clean way. So this is where something that sounds probably very, very strange to a philosopher, which is, I think part of the art of being a theoretician is to have a good taste in problems. So meaning that you have to figure out if something can actually be calculated, whether you can make a prediction, whether this idea can be confronted by data, and so on and so forth. So you go through that thought process, which I think is not unlike how a philosopher would feel out a problem.
Yeah, definitely. That's an interesting parallel. The primary focus of your research is on exoplanets, as you mentioned. And an exoplanet, if I'm correct, it's just a planet orbiting a star that is not in our solar system.
That's correct.
Right? That's correct. You are not an observer. You're not an instrumentalist. Well, was that the word that you used?
An instrument builder. Yeah, I'm not an instrumentation person, that's for sure.
An instrument builder. So I was wondering, what physical tools that the instrument builders use or build that the observers are using give you the data that you work with? Is it like the James Webb or the Hubble Space Telescope, or?
So since exoplanets, everything in the cosmos is really far away, right? So
very far.
Our chances of traveling to the nearest star using current technology is basically zero. We can't do that.
Yeah.
So all of our investigation has to be done by studying the light that comes from these distant objects. We call it we call it remote sensing. And so a lot of the light comes and if you split the light into colors, that's called a spectrum, right?
Right.
And one of the great breakthroughs of astrophysics over the last century or so was to figure out that, first of all, these wiggles and dips you see in the spectrum are not random. They're caused by atoms and molecules and ions absorbing light at predictable wavelengths in a predictable way that can actually be calculated to great precision by quantum mechanics. And also, astronomy has demonstrated that the same laws of physics that govern atoms and molecules on Earth behave the same way in other parts of the universe. And so that's very convenient. So it means that if I could record a spectrum of an exoplanet, and I could actually compare it to objects in our solar system, I could try to learn something. Right? So to answer your question, the engineers would build telescopes like the Webb with instruments known as spectrographs that would record the light and split it into different colors and therefore give us spectra to think about. Then my job as a theoretician is twofold, right? Because these spectra and the way that atoms and molecules absorb light across wavelength obey the laws of quantum mechanics, I can actually use well-defined physical laws and principles to actually calculate what this looks like. So that's a lot of what we do in my group. So you can convert a spectrum into basically, you can take a spectrum and turn it into, this planet has this much water and this much methane and this much different types of molecules, right? But there's a second step where I think the theoretician's input is important, which is after you get this amount of water and methane and whatnot, so what, right? What does it tell you? And so this is where the interpretation comes in. And I think to answer the question of, is there biochemistry on other planets, you have to answer the really important question of, what are the false positives? What are the things that have nothing to do with biochemistry that could fool you into thinking that is biochemistry? And in planets, that turns out to be the geochemistry. So rocks are very talented at making gases that could fool you into thinking they come from life.
Yeah, I saw that you just had a paper come out with the geochemist Meng Tian
That's right.
on the geochemical baseline that provides false positives for future biosignature searches. Or you thought that that's what the James Webb Telescope would be very, very useful for in the coming years?
I think so. I think the James Webb is not going to detect biosignatures or remotely sense evidences of biochemistry. That's what biosignatures are. I don't think the Webb is going to do that. But I think the Webb can teach us about the geochemical baseline that's produced essentially by geology, by rocks. And I think biosignatures are anomalies, and to define if something is an anomaly, you need to define a baseline. So I think that's the step that a lot of people in my community are not paying attention to. I think we should do that step before we talk about biosignatures. But I think talking about this topic gives you a sense of how a theoretician thinks. And in a topic like exoplanets, you can't just think like a physicist. You have to pull in different disciplines to answer these questions.
So to return, though, to that question that I asked, I'm curious about which particular telescopes and radio arrays, perhaps, that you're using. So you're using the James Webb. Are you using the Hubble Space Telescope, or what are the other arrays that you're using?
I think it's more accurate to say that I work with people who know how to use James Webb and Hubble data. I don't do it myself.
Okay.
So I participate, and I and my group participate in the data interpretation step of that process.
The observers collect the data.
Exactly.
And then they send it to you. But which other telescopes and arrays are you using data from?
So we use the Hubble. We have data coming from the Webb for sure. We have data coming from telescopes on the ground with very big mirrors. Like there's a European telescope called the Very Large Telescope, the VLT, a very imaginative name, with an 8-meter mirror. Europe is going to build something called the ELT, the Extremely Large Telescope, which has a 39-meter mirror.
Okay.
I think it's Dutch
very
humor.
Extremely large.
And these ground-based telescopes, they're a big part of the landscape as well.
Now, aren't there limitations, though, because of atmospheric perturbations that prevent you from getting... That's why the stars seem to twinkle when we look at them, because of the atmospheric perturbations. But how is it that... Does it have something to do with the wavelength that these telescopes on the ground are detecting that enables them
Absolutely.
to... Okay, so what is it that enables you to use these ground-based telescopes in a useful way when they're not?
Absolutely.
In the sky?
I mean, if you use telescopes on the ground and you're trying to detect water, the problem is that our atmosphere has water too.
Yeah.
And so if you just took a snapshot of a system, so you would get contributions from the planet, the star, and our atmosphere.
Right.
What actually saves you is if you record the movement of the planet as it goes around its star. Then as the planet goes around in the orbit and goes, towards and away from you, the light reds and does a Doppler shift. So meaning the light that's coming towards you, it gets a little bit bluer, and the light that goes away from you
because the
gets a bit
wavelengths
redder.
compress or extend.
You're right. The wavelengths get longer or shorter, and once you have this time dependent information, what happens is that the water lines from the planet's atmosphere. They do this back and forth dance relative to the other lines. So if you have time information, you could separate out the contribution from the planet. And this is not a technique that I invented. This is a technique invented by
it's pretty brilliant,
astronomers in the field. So astronomers are very careful about this, and they have been very creative at finding different ways to tease out the effects of the atmosphere.
So you're still able to take useful spectral readings from ground-based telescopes.
Absolutely.
Then what is it that makes a space-based telescope more useful? Are there things or not more useful, but differently able? Can it do things that a ground-based telescope can't do, and vice versa?
I think that's difficult to answer without being too technical, but I think the short answer is that because you're above the atmosphere of Earth, the spectra that you record tend to be more precise, meaning that it's not so noisy. It's the uncertainties around each data point is smaller. Whereas on the ground, the spectra you record is noisier. But because it's on the ground, you can build a bigger instrument. You can actually collect more data points across wavelengths. So your resolution is higher. So there's a trade-off between the ground and the space. Okay.
And then we've already talked about one theoretical tool that you use to interpret the data. We talked about the spectral readings, which anecdotally, when I learned about this, it totally blew my mind. So I took some astrophysics and astronomy in undergrad because for a while I wanted to be an astrophysicist and I thought I was going to major in it. But I went to like a meeting with some graduate students and they spent the whole time going over equations governing like potential models for how stars are born in early in galaxy formation, and I just found this very boring. I wanted to like discover what dark matter was, and that turned me off. But anyway, as a kid, I remember being absolutely blown away by the Hubble Space Telescope images, as so many people were. But then I felt totally hoodwinked when I learned about spectral readings and the fact that many of those Hubble images are captured in maybe X-rays, for instance, and then the light is, well, I don't know how you would say it.
It's a false color. It's not the color that your eyes would see. So they will combine optical light that Hubble measures. Hubble also measures ultraviolet light that we can see. So you need to use a false color, and you probably combine that with data from the Chandra Space Telescope, which is X-rays. And so you would lay them out in different colors, just so it's false color. It's not real color.
So if you were looking at it with your eyes, you would not see anything like these pictures. And Absolutely. I found that very sad and disappointing. It'd probably just be, I don't know what you would see if you'd looked at a quasar or something, or a pulsar or something like that, a binary star.
You get used to it because after a while, when you're a professional astrophysicist and you look at these images, it's not the exact color that's important. I mean, it's the fact that when you look at different objects in X-rays and UV and optical and infrared, you're probing different structure, and it's the information on the structure that's actually interesting. Of course, in the popular imagination, false colors are misleading.
Yeah.
So when I first realized that, I was I think disappointed as well. I felt slightly misled, but then I realized that wasn't the point.
So, but there is an interesting, I think, philosophical dimension to the false color images in that it's a reminder that what we see isn't necessarily how the world is. I mean, there is so much happening beyond what we can see, and obviously, I mean that's obvious on a microscopic level. Like, I mean, this is composed of plenty of very small things that I can't see. But even on the macroscopic level, when we look at the night sky and we just see some little dots that are stars, there's actually so much more happening that we can't see just because of how limited we are with the wavelengths that our eyes can process.
Well, I think about it. I mean, as someone who actually, I specialize in a branch of physics that's used a lot in astronomy. It's called radiative transfer. It's how radiation interacts with matter, and so that it will produce the type of light you see.
Yeah, I was
that's
actually going to ask you about radiative transfer because I was reading from your book, Exoplanetary Atmospheres, Theoretical Concepts and Foundations, which you did with the Princeton Series in Astrophysics. And radiative transfer you had 2 chapters on radiative transfer. So it's clearly very important to studying the atmospheres of these exoplanets. So I know I cut you off, but maybe you could say more specifically what the radiative transfer is and why it's particularly relevant to the exoplanet research.
I think it's a branch of physics that teaches you. So you talked about false color, and this is why it came up, because if you look at the sun in X-rays versus UV versus optical light, you will see that not only is the size of the sun slightly different by a very tiny amount compared to the entire radius of the sun, but you will see that the structure that shows up is different. And the reason is because different, forms of matter is not the correct word. You're probing matter at different temperatures, at different ionization states, and therefore at different colors of light, they would be transparent or opaque to different degrees. That's really what radiative transfer is, right? Mm-hmm. So if you look at a cloud in the sky at certain colors of light, it will look opaque, and if you look at a cloud at different colors, it will look transparent. And that's what false color images in astronomy are meant to convey. They're meant to show you how opaque or transparent light is at different wavelengths, different colors, where you can think of the entire spectrum of light from the X-rays to the ultraviolet to infrared as a generalized form of color. Mm-hmm. And so you're studying how matter becomes transparent, opaque, and therefore exhibits different structures. And by studying that tells you something fundamental about the state of matter in these objects. And once you realize that, then you realize that actually false color images have a lot of information encoded in them. Mm-hmm. And that's why astronomers take spectra, or they take images at different wavelengths, right?
We've talked a bit about spectral readings. Another tool that I saw that you use to interpret the data is something called gravitational microlensing. And I'm familiar with gravitational lensing because it was so famous for confirming some of Einstein's predictions. But what is gravitational microlensing, and how are you using that?
So this was predicted by Einstein, but then he, if I remember correctly, he dismissed it as an effect that was too small to be seen. Then the person who really pioneered this was a Princeton professor called Bohdan Perchinsky. And basically the idea is that if you had a star very far away in the background, and you had another star go in front of the star, and the distances between the two stars can be many light years, then the star in the foreground, which is the so-called lens star, can act as a gravitational lens. It can actually, as the star, stars are not static; they move around. So as the star in the foreground aligns itself in a correct way in front of the background star, you see a transient brightening of the light. That's gravitational lensing. The reason why it's called microlensing is because it occurs on micro arc second length scales, and you can use that to detect planets, because if the foreground star has a planet around it, this creates the distortion in the lensing pattern that you can then detect, and if you analyze, you can figure out what the mass of the planet is and so on.
Okay, so it's useful for discovering the planets, but it's less useful for determining the quality of their atmospheres?
That's correct. You get no information on the atmospheres.
Okay. Now, are there any other important tools beyond the spectral reading that are particularly relevant to the exoplanet research?
The technique that's really relevant is the transit method, because you can do repeated measurements and you can follow up with telescopes like the Webb, and you can get spectra. And the other method that's really important is something called the radial velocity method, which is, as the planet orbits the star and the planet well, you're always taught that when a planet orbits the star, the star is static and the planet orbits around it. But what's really happening is the planet and the star orbits around a common center of mass. But because the star is so massive, the center of mass is actually inside the star. And so as the planet goes around the star, what the star does is it does this little tiny wobble back and forth around the center of mass. And astronomers have become really good at measuring this. So my Swiss colleagues were very good. They're world-class at measuring this. And this radial velocity method essentially provides the mass of the planet. And the transit method provides the radius. And both methods can be used to study the atmospheres if you have wavelength information.
And so what then has your work really focused on with regard to the exoplanets?
Oh, that's also tough to manage. So I'm generally...
Are there any particularly important discoveries or contributions that you and your teams have made?
So we've worked on many things. Generally speaking, I'm a generalist of sorts. I'm led by questions, and then I pick up the skill set needed to study these questions. But I started out very interested in just how do you use fundamental laws and principles of physics to calculate these things. So this includes things like radiative transfer. How do you calculate the nature of light passing through an atmosphere? How do you calculate the chemistry? So what type of molecules are produced at what temperature and in what proportion? How do you calculate how the atmosphere is mixing and swirling around, right? Atmospheric dynamics. So I was interested in things like that. But then we became also interested in interpreting data. So the idea is, how do you do inverse modeling? So meaning, how do you go from a measured spectrum to inferring what the chemical abundances are? This is called inference. And then this opens up, once you go down the rabbit hole, you start thinking about Bayesian techniques and how do you solve inverse problems. I also spent a lot of time interpreting between theory and observations, so serving as sort of the translator between the two. For example, there was a Swiss telescope called Cheops. It's still in the sky, and we studied how, among other things, we studied how a planet reflects light from the star. This started with the study of the moon. As the moon goes around the Earth and you see different phases of the moon, you could ask the question, how is the light from the moon being modulated, going up and down as the moon goes about shows you different phases. This is called a phase curve. And it turns out that if you study the shape of this curve, you could work backwards and you could say something about the scattering properties of the moon. This was done by lunar scientists in the 80s. There's a very famous one, a person called Bruce Hepke, who did this. So one of my contributions to this field is I solved this mathematical problem in a general way. So it was the solution to a 105-year-old problem. So this phase curve problem. So that was one of the contributions. I guess now the most recent contribution is basically this idea that you could actually write equations down and calculate how the geochemical outgassing of a rocky planet in a way that can be tested by data. So this is something very new. So it's hard to tell you one. It's really hard to summarize to you one singular achievements we've done. I've sort of floated around. We've done many things, but I'm primarily interested in how you can use the laws of physics and chemistry to relate to what you see.
Mm-hmm. And it sounded from what you were saying earlier, and based on one of these important things you hope to get out of the James Webb, that a major motivating factor in your research is the search for life outside of Earth. Is that accurate?
I think the field of astronomy and astrophysics as a whole this is one of the grand challenges of the field, that we really hope to find signs of biochemistry, biosignatures on other planets. I come at this problem in from a very different angle, which I think I described earlier in this conversation, which is that the reasoning is as follows: whether a particular gas is a biosignature or not depends strongly on an atmosphere. So you can't just go out and look for oxygen or ozone, because there are other ways to produce oxygen or ozone that have nothing to do with life. Like, for example, you could have a planet with a lot of water. The water could be broken up by photolysis, so ultraviolet light, and this breaks water up into hydrogen and oxygen. And if the planet has the right conditions, the hydrogen escapes and the oxygen stays behind. So you suddenly have an oxygen-rich planet that looks like it's teeming with life, but actually has nothing to do with life. So that's one example where your interpretation of what a biosignature is depends on your knowledge of what the rest of the atmosphere contains. So if you go down that route, then you will realize that in order to understand what a biosignature is, you have to understand what the background atmosphere is. And if you look at the solar system, this already gives you a very important clue. If you look at the solar system, there are two types of planets. You have the gas and ice giants, right? So Uranus, Neptune, Jupiter, and Saturn. And if you're very generous with your interpretation of the chemical abundances, and you're not too picky, you'll find that these four ice and gas giants look somewhat like the sun. They're mostly composed of hydrogen, helium, with some metals. But if you look at Earth and Venus and Mars, the atmospheres look nothing like the sun. And the reason why they look nothing like the sun is because it has less to do with the history of how they form and more to do with how geology is influencing these atmospheres. So outgassing, geochemical outgassing.
Yeah. Maybe like Enceladus, even though is that a good example?
Well, Enceladus is a moon. Yeah.
Right, but I just picked that because it's literally outgassing all the time.
Yeah, Enceladus is a moon. For example, Venus is mostly carbon dioxide, so is Mars. And Earth is 78% nitrogen, 20% oxygen, and trace amounts of water and carbon dioxide. So this is the way we are attacking the problem. We are coming at the problem not as saying, how do we prove there's life, but what are the false positives that could trick you into thinking that something is biological?
And what are some of the typical biosignatures that you're looking for?
As I said, nobody knows. It depends on the atmosphere.
Okay.
But that's exactly the point I'm trying to make. There are two schools of thought. You could look for specific biosignatures based on very Earth-centric ideas.
Yeah.
But in the history of astronomy, we have seen that most of the time when we actually have data, it looks very different from our preconceived ideas. Mm-hmm. The second approach is to look for biosignatures as anomalies from a baseline. I see. And that baseline is geochemical. And that's the reason why we study geochemistry. So the second approach has the philosophy that we don't know exactly what we are looking for. We're trying to look for anomalies. And let's study what the abiotic background is doing first.
Okay, if you were looking at Earth, though, what are the biosignatures that would give away that there was life here if you were on a different planet? The standard classical narrative of Earth is that you look for oxygen and ozone and methane and carbon dioxide, and if you analyze these abundances, you'll find that they're out of chemical equilibrium. That's the classical narrative that has been told for decades. But it is entirely conceivable that the planets you find out there will behave differently from Earth. And so the search for extraterrestrial life is one motivating factor in the exoplanet research. But as I was reading your book, and I saw that there was so much work on oceans and other familiar geological phenomena. I was wondering if in studying these other planets, there's also a sense in which we're studying Earth, because different planets with different atmospheres, sizes, oceans, it tells us, I guess, what Earth might have been like or what it could be like. For example, if we find a planet with a higher concentration of CO2 that is otherwise, I don't know, in the Goldilocks zone or has similar spectral readings to what we'd expect from Earth, we might be able to discover properties that might tell us something about the impacts of global warming, for instance. Are any of these reasonable conjectures to make about what you're doing?
I think it's far-fetched. I wouldn't go so
Okay.
far to say that I could study exoplanets and say something about Earth. I think that's something we tell for, I don't know, for public relations, but I think it's far-fetched. I would say one challenge of exoplanet science is that it's really difficult to know to what extent one can generalize beyond what we see on Earth. I think the most useful way to think about it is that for Earth and the close-like planets like Venus and Mars, we have a lot of detailed information and data that we can use to study physical and chemical processes. And we don't have that luxury with faraway exoplanets. So I think the opportunity with Earth and the solar system planets is to study physical processes and hope that this we can then understand these processes well enough that we have some confidence that we can apply the same processes at work in planets that are far away. This is a very difficult undertaking. It's always dangerous when one extrapolates.
Yeah. Before we move on to some of the more philosophical concerns, are there any things going on in the exoplanet research that you're not involved in right now that have you particularly excited?
I think the web overall is very exciting. So I'm not involved. I'm certainly not involved in everything that goes on with the James Webb. It's a large community of people. So I think it's exciting how people are figuring out very creative ways to take and analyze and record data to test out the instruments and so on. I think there are some exciting space missions coming up, next generation space missions that are being planned by various teams around the world.
For the purpose of studying exoplanets?
Yes.
Oh, wow.
The extremely large telescope that you mentioned has a strong exoplanet component as well, which I find very exciting as well. And yeah, there's a lot of theory work that's very exciting, but I don't know how to condense it all to summarize it.
That's fine. So the way that, as I mentioned when we were talking before we started, that I came upon your work was because you tweeted about editing the first ever anthology on the philosophy of astrophysics with three philosophers. I might pronounce their names wrong, but Vera Matarese, Nora Boyd, and Siska de Baerdemaeker. And how did you get involved in this project?
Oh, that's an interesting history. So, as I mentioned to you, I was the director of Interdisciplinary Center in Switzerland when I was in the city of Bern, when I was a professor there. And the university gave us the mandate that we needed to stimulate interdisciplinary research. So I started talking to different academics outside of astrophysics. And I started talking to the philosophers. In particular, there's a professor there called Klaus Beisbach, who specializes in philosophy of science. Then a few years later, we decided that we would hire an independent postdoctoral fellow to stimulate the link between astrophysics and philosophy of science. And that person was Vera Matarese, whom you just mentioned. She's Italian.
Oh, is she Italian?
She's Italian.
Cool.
She's an extremely good colleague, and she's extremely good at communicating and translating between philosophers and astrophysicists.
Okay.
So then as the pandemic hit and everything went to Zoom, Vera had the brilliant idea of organizing something she called the philosophy cafe. So every week we would spend 2 hours on Zoom, and she would review some paper in philosophy of science, and we would talk about it. And the two people that kept coming to the Zoom calls, even though they didn't belong to the university, was Nora Boyd and Siska. I can't even pronounce the last name, De Baerdemaeker. And so they kept attending, and we kept having this really interesting, really deep conversations about various aspects of philosophy of science. I'm particularly interested in epistemology, the philosophy of knowledge and how we understand things. And so lots of conversations were centered around that, the nature of models, the nature of simulations, and so on. And after, I would say, about 1 to 2 years of conversations, we started to know each other better, and this led to the volume. This is how things evolved.
Before we talk about the models and your thoughts there, what were some of the broader questions being addressed in this volume by philosophers?
Gosh, I don't remember the contents off the top of my head. There were 13 chapters. I think there were a few articles about black holes.
Oh, that's very cool.
There was a whole section essentially on realism, is what I remember. How basically, how can we tell if something is really as it is in nature, or is to some extent a mental construct? And what I found interesting was the ideas that philosophers had about models and simulations. That's also in the volume. And something that philosophers call fictions was also fascinating to me, because we think about it very differently.
Yeah.
So there were aspects of that I was interested in.
So maybe we should just start with, what is a scientific model? How do you think of the term? Because models are used very differently in different domains. So a mathematical model is very different from an astrophysical model.
Yeah, I think it's difficult to reach consensus to get a broad definition of what that means, because a model in, say, geology would be very different from a model in astrophysics, would be very different from a model in economics, right? A lot of models use mathematics, but I think it's important to distinguish between math is a language, and it's important to distinguish between models that are based on what we call first principles, meaning that they derive from governing equations of physics, rather than something you just made up just because it fitted the data, right? Like an ad hoc model. I would call that a pseudo model. I guess the way I think about it is, where should I start with this? So there are governing equations of physics, right? So that's like the Schrodinger equation for quantum mechanics. So I guess one has to distinguish between a theory and a model. And from my perspective, a theory is a field of physics where we have certain laws and physical principles, and the starting point is some governing equation of physics. Like, for example, quantum mechanics has the Schrodinger equation, fluid dynamics has the Navier-Stokes equation, and there's an equation in radiative transfer, and so on and so forth, right? Mm-hmm. And I think a model is fundamentally a solution that comes out of a governing equation that is designed to answer a specific question. And I think I emphasize that because I think one of the misunderstandings that people have is that they confuse precision and accuracy, and people think that a model is like a black box where it emulates the world in all of its detail, like the Matrix, right?
Yeah.
So you could emulate the world down to every detail, and therefore, if you could ask any question you want of the model, and in practice, this doesn't exist. And I'll give you an example, right? So, for example, if your scientific question is, what is the microscopic structure of water, H2O? You would turn to quantum mechanics and you would solve the Schrodinger equation. But if your scientific question was, how does water behave on large scales, and what type of waves does it produce? Is it gravity waves or some other type of wave? Then you would actually solve the fluid equation, right?
Mm-hmm.
So if you try to answer this wave behavior by looking towards the Schrodinger equation, then you have the wrong theory and you will construct the wrong model.
Right.
And likewise,
so it's very task dependent.
It's very question dependent. And I emphasize that because it is the job of the theoretician to understand when the model breaks and what question you're not allowed to ask. So I'll give you another example, right? Have you ever wondered, we don't really know what dark matter is,
mm-hmm.
and yet there are very large scale simulations that study the cosmological structure of dark matter, right? And how's that? Why is that? How are we able to claim that we understand the cosmological influence of dark matter without actually knowing what dark matter is? And this is because these simulations were constructed in such a way that you're not allowed to answer scientific questions below a certain length scale. So as long as you do not ask scientific questions that are at a microscopic length scale that forces you to understand what dark matter microscopically is,
mm-hmm.
then this model and simulation is valid. And this is really
right.
important. And this is something that is really misunderstood by a lot of scientists and misunderstood by the public. Models are constructed to answer questions. And it is the job of the modeler to understand what question you can or cannot ask. And this leads me to something else in the volume that one of the philosophers talks about, which is something called fictions, right? This philosopher, whom I should not name, was saying that essentially, for example, stars are not spheres, but by assuming that spherical symmetry, that stars are perfect spheres, that you're introducing a fiction into your model that doesn't really exist, and this was frowned upon and thought of as a serious flaw.
In the paper?
In one of the chapters.
Yeah.
But again, this really depends on your question. If your question is, how do stars evolve on cosmological timescales, right? Then the assumption that the star is a perfect sphere is not so bad. It's not terrible at all, compared to the model predictions that, in terms of the model predictions that you will make to compare the data. It's fine. But if your scientific question was, how do stars distort themselves as different sound waves run across it, also known as astroseismology, then you wouldn't make that assumption for stars. You wouldn't make the assumption of spherical symmetry for a star. The point is that every equation in nature and every model has approximations baked in.
Mm-hmm.
And figuring out which approximations you can tolerate and which approximations not is part of the art of modeling. And it's tied to the question you're asking.
So would you be opposed to describing your view as one that endorses these models as useful fictions in certain cases, or you just don't want to use the fiction word at all because of maybe the analogies it draws? Because it does seem to me like you're what we might call an instrumentalist about certain models. You don't want to be committed to stars actually being spheres, but you, within the model, will entertain this idea because of its use in answering a question.
I think the very use of the word fiction just conveys a fundamental misunderstanding of what models are used for. Because the individual that thinks of a fiction in a model essentially has an extremely mechanistic understanding of the world, where every phenomenon in the world can be understood as a large collection of essentially billiard balls. and that in order to understand the world, we have to calculate everything to like an arbitrary number of decimal places.
Mm-hmm.
But that's not the way that scientists use models to understand the world. Let me give you another example, right? So, how do we model disease transmission? COVID. This was a hot topic, during the pandemic, and so I published papers on this. I published 2 papers with epidemiologists on COVID modeling.
Oh, really?
And in fact, you use fluid equations of mass conservation. No one believes that human beings behave like a fluid, right?
Right.
So, certainly nobody believes that. But if your scientific question was, how does disease transmission occur in ensembles of human beings on scales of cities, then these ensemble of human beings can be approximately described by a fluid that conserves mass. And the R number that has been in the media, and the reproduction number of the disease, is not just how intrinsically infectious the virus is, in this case COVID, but it encodes our things that we cannot really model. Our ignorance about how individual humans interact. Do they hug? Do they keep a distance? How often?
Mm-hmm.
How long do human beings keep in contact, and how far do they stand away from each other? These are things that you cannot model. And so these are things that are captured in the R number. And this is what I mean, right? Do you call a COVID transmission model that works extremely well, do you call these things fictions? I call them approximations. And I call them approximations because every single model has an approximation. And every single governing equation of physics has an approximation. This is the reason why I do not understand that term.
Well, an example that comes to mind for me is in economics. Certain economies have been modeled using non-standard analysis, in which to sort of capture the sense that no action of an individual will have an effect on the economy. They're treated as infinitesimals. And yet the person who makes this model doesn't want to admit infinitesimals into their sort of ontology, so they'll treat it as a useful fiction. But and they'll be an instrumentalist about the use of these infinitesimally small quantities. But I understand what you're saying when you don't want to use the term. It's fiction just seems like a category mistake. It's a calculating tool. It's an approximation. Now, one of the things you mentioned for what makes a good model is whether you've chosen the right theory to answer the question you have, right? So if you're asking about water on the small scale, you'll use the Schrodinger's equation, and that'll produce a good model. And then one way you can get a bad model is by asking, in the case of the dark matter, by asking something about dark matter on a scale where you don't have a theory that can give you a good model. Is that roughly accurate so far?
Yep.
What are some other things that will tell you if the model is good or the model is bad? In your essay that you wrote for the volume, you mentioned the Human Brain Project. So how does that tie in?
I mentioned the Human Brain Project because there's a school of thought that if I build a big enough computer and I throw enough stuff into it, that I can essentially understand anything I want to arbitrary precision. And I think even leaving aside the logistics of it, I just think that fundamentally this is not the case. And there are several reasons for that. One reason is that you fundamentally do not have enough resolution. So you always run out of resolution. This is called dynamic range. So you can never simulate the full range of length scales to turn a simulation into an actual experiment, like in nature. The other fundamental reason is that governing equations of physics are usually written in a continuous form, but to put them into a computer, you have to discretize these equations. And this introduces, without going into too much detail, essentially numerical knobs that weaken your ability to predict. So I think when I read what philosophers say about simulations, I think they have in their mind this very exact predictive machine that's going to give you a very sharp answer. But I think in reality, for almost without exception, simulations always have incomplete physics because you never resolve the full length scales. And because of numerical challenges, they always have these ambiguities. It's not sharply predictive.
Right.
Those are two very fundamental problems that I think are overlooked. The other thing about a simulation is that if you're really conservative, what a simulation does is that it shows you that, say, some state A or some point A becomes state B or point B. You produce a correlation. You say that A is correlated to B. But really, as a scientist, what you're interested in is whether B is caused by A, if they're causally related. And usually we establish that in that we can't use the simulation itself to completely establish that. We actually need a theory. We need to construct a simplified model, at least in astrophysics, to then turn that correlation into causation. And the thing with the Human Brain Project, if you read articles on it, I'm not a neuroscientist, is that the philosophy behind it seemed to be that if I just simulate enough neurons, then I could basically completely replicate how the entire brain functions. That all of this, what is thought to be emergent behavior about the brain, would just magically appear. Mm-hmm. And I didn't have to construct this with a scientific question in mind, which is something we talked about earlier. I just had to construct a giant numerical laboratory that I could ask any question I want of it. And I think, I don't know how many billions of euros they spent on it, €1 billion, I guess, or more. So a lot of money, and more than a decade later, this did not come to fruition.
Oh, wow. Not at all.
It just didn't work.
Oh, wow.
I think there are plenty of articles on the internet that would describe to you reasons why it didn't work better than I can. But fundamentally, it goes back to this thing I tell you, which is that in practice, you can't construct an emulation of the world without a scientific question in mind. It's a philosopher's fantasy. It just doesn't exist.
Does this at all relate to what you've called the verification and validation framework for models?
Oh, that was just a small criticism. I think the idea of validation, at least in that part of the literature, is that you couldn't really validate a simulation till you compare it to some kind of ground truth, like a mathematical ground truth. But to me, the argument is circular because, and the reasoning is because most of the interesting phenomena in nature comes from mathematical solutions that are non-linear. And exact non-linear solutions that you can write on paper are very rare. Mm-hmm. And it's because they're very rare is the reason why I turn to a simulation in the first place. As a practitioner, I turn to a simulation because I'm unable to write the exact solution on a piece of paper. So I simulate it in a computer. So it's a circular argument, right?
Yeah.
So how do I validate a solution using something I can write on paper when that's the reason why I turn to a simulation in the first place? Mm-hmm. That was all I was trying to point out.
You mentioned in your article there in this essay in the volume that there's a very fascinating unsolved problem about turbulence that hasn't received much attention from philosophers of science. What exactly is the problem with turbulence?
What I find fascinating about turbulence is that you have all of the tools at your disposal. So you know what the governing equation is. The fundamental governing equation is the Navier-Stokes equation. Therefore, you can use the equation to simulate turbulence in the computer. You can do lab experiments, and you can produce a whole family of fluids that look turbulent. And yet, decades of research later, we don't have a fundamental understanding of turbulence. And what I mean by that is that, for example, one of the questions is, how do you transition from fluid behavior that is laminar, so well-behaved in well-behaved layers, to something that's turbulent?
Mm-hmm.
And this transition is usually characterized by something called the Reynolds number, the details of which are not so important. And if you had a real theory, you could predict the Reynolds number at which every phenomenon would transition. And you could predict it irrespective of geometry or circumstance or setup. And we don't have that. We just don't have that. All of this is very experimental. We see in experiments, we see that this Reynolds number changes with different geometry and different setups, but we don't have a theory to understand why. We can predict that phenomenon. And I find it fascinating because it's not like dark matter where you don't know what dark matter actually is microscopically. Here, you know what the fluid is made of. You have the equation that describes the macroscopic behavior. You can simulate it, you can do experiments, and yet we don't understand it, right? And I think this tells you that there's something missing in our thinking. I don't know why it is, but we have all the tools and we don't have the answer.
What is the sort of contribution you might expect were philosophers of science to pay more attention to this problem? Because in your article, you mentioned that it surprises you that they haven't devoted much attention to it.
I think that's hard to answer. I don't think I can make any specific recommendations. What I would say is that I always found it useful when, in astrophysics, it is always useful when theoreticians, who are more like philosophers, and observers, who are more like astronomers, and experimentalists, when they interact, so that there's an iterative exchange between theory and data. And I cannot help but think that some wonderful things would come out of philosophers of science interacting with practitioners, specifically theoreticians like myself. And think that interaction is going to lead to different questions, different ways of asking the same question, paying attention to different issues, and so on. At least that's what I've gotten out of the interactions with the three philosophers. I don't think it's a one-way thing. I've learned a lot from them, and they have gotten some input from me as well.
I saw that you are a culinary school graduate, and I saw on Twitter that you're always posting these very delicious meals. How did that enter into your life?
In between, so when I was doing graduate school at Colorado, I had already been cooking for a long time. It was always an interest and a hobby. So in between my master's and my PhD, I think I felt a little burnout and a little bored, so I wanted to do something else. And there was a culinary school, a professional culinary school, very close to where I lived in Boulder, Colorado. And so I would just, leave the office at 4 every day for 6 months, well, a few days a week, and cook for 6-7 hours.
Oh, wow.
And after 6 months and I think roughly 600 hours of cooking, I don't remember, it's long ago. Basically, I got this diploma from the culinary school. It was also a career backup plan in case academia didn't work out. Mm-hmm.
Now, I this is sort of funny. I just watched this movie. You've probably heard of it, called Crazy Rich Asians.
Sure.
That takes place in Singapore, and the street food, at least as they depicted it in this movie. Have you seen it?
I've seen it. I don't remember a lot of it. I remember the impression that it was a caricature of Singapore.
Yeah, I believe that. But the street food, looked absolutely amazing. And I have a friend here who also went to Princeton, and he's from Singapore. And he told me that the street food is exactly as they portrayed it in the movie, that it's just like totally like awesome street food, just people like perfect it for generations.
Absolutely.
Is that some of your favorite food in the world?
I think so. I think there's something very wonderful about just doing one thing, one dish, and doing it so well, for generations that a normal cook like me just can't replicate it.
Mm-hmm.
I think that's something wonderful about that, and you find a lot of that in the street food of Singapore.
Do you have any dishes that you cook a lot like that, though, that you're particularly proud of?
I don't think any of it rises to that multi-generational level, but I like cooking curries,
Okay.
and the training in culinary school was French American training, so we could basically cook a lot of things. Yeah.
Well, this is I haven't ever asked on the podcast questions about gear advice, but what is your favorite and most useful kitchen tool? I'll say mine. Mine are, the brand Global that makes knives.
Sure.
Yeah, I have. They have shears, like scissors, and my Global shears are just absolutely amazing. They cut through anything, so I'm very happy with those. But if you have anything awesome in mind, my kitchen could probably use it.
Well, the way I was taught is very very old school, I guess. So the way we were taught in culinary school was, if you're a good chef, you could do everything with one knife. So just a standard chef knife, and you don't need anything else. Essentially.
What chef's knife do you use?
Oh gosh, I don't remember the brand. It's a German brand. So, it's a German knife.
Probably Wusthof.
Probably. I'm not super sure, but probably yes.
Okay. And then the last thing I was curious about is, this is evidently important to you because it's in your Twitter bio, but your profile says that you adore Bottega Veneta.
Yes, absolutely.
Yeah. So what is it about Bottega Veneta that you love so much? Is that what you're wearing right now?
No, it's not. But I think we as scientists and academics, we spend a lot of time, in our heads thinking about very blue sky thoughts about rather serious things. And it's just nice to have a side that enjoys the more frivolous part of life, right? Mm-hmm. So I think there's always this stereotype that scientists don't care about how they look and they don't dress well, and I think it's nice to do that sometimes. Mm-hmm. The reason why I like Bottega is because they are the brand without a brand. So they produce things with no logo, no emblem, no description. So you look at the thing and you have no idea what brand it is, but you can tell that it's made very well. At least that's the philosophy of the brand. So you don't know what you're looking at unless you're one of the insiders that knows that this thing exists, right?
So is what attracts you to it the construction more than the design? So I don't know Bottega Veneta's design so much, but I know that brands like Bottega Veneta or Loro Piano or Brunello Cucinelli, they have really top level construction and materials.
Absolutely. Yeah, it's exactly what you described. The quality, the quality of the craftsmanship, the quality of the materials, and to me, that's just something about. I guess it's the opposite of fast fashion, mm-hmm. which I have a lot of issues with. The treatment of people, the treatment of the earth, the treatment of materials, and so on. And it's the exact opposite of that, and it's really nice. I guess I take joy, just like in cooking or in science or everything else, when you see a piece of craft and you know that this individual, this craftsman, has gone above and beyond to ridiculous length, mm-hmm. beyond what is reasonable to a normal person to perfect that craft. And it's just a pleasure to see something like that.
Mm-hmm. So am I right then that you're more interested in the craftsmanship than Absolutely. The fashion, than the design? It's
both. I mean, they are related, right? It's not. It's it certainly has to be high quality, it has to be functional, but it has to, for lack of a better word, it has to look good. But that's a very subjective phrase, right?
Yeah.
Yeah. I don't know how to put it. I don't like things that are
Okay.
loud and obvious when it comes to clothing.
So when you say look good, you mean maybe something that more just suits your body type and fits you well, that sort of thing, as opposed to wanting like something like a Dolce & Gabbana thing that screams what it is.
Exactly. Something that augments who you are, rather than something that screams from your chest, like you were saying, that draws attention to you, and it's very personal, right? I mean, different people have different takes on this.
Mm-hmm.
Yeah, I don't know what your take is, but yeah.
Yeah, no, I'm. Well, I mean, I wear a lot of T-shirts, and they're like $2 or $3 T-shirts from Gildan. If I had a lot more discretionary spending, I'd probably buy some nice T-shirts. But I do occasionally spend money on things like Japanese denim, which you probably know is some of the best denim. Or I like a lot of Japanese clothing because of the care they put into construction, particularly military reconstruction garments or reproduction garments. So there are brands like the Real McCoys that will custom make everything from the threads to the rivets to the buttons, and get dead stock zippers, because they're very, very much perfectly trying to emulate something that's 70 or 80 years old. And like you mentioned, I mean, it's the same thing as the food that's being perfected for generations, or the craftsmen at Bottega Veneta or Loro Piana. Just having something that's been imbued with this much care is it can bring a lot of joy to your life just by having something like that on your body.
Yeah, absolutely. And I think this is a sort of a life philosophy that also affects I guess I approach science and other things in the same way, which is I really appreciate it in other people, other craftsmen, other professions, when something is deep, not shallow, when you see that a lot of thought has been put into it and it's understated. There's no need to scream about it to the whole world, because the quality and the thought that went to its construction speaks for itself.
Mm-hmm.
So I like things like that.
Mm-hmm. All right, well, that's, I think, a really great way to end. So thank you, Kevin, for being my first astrophysicist on the show. This was so much fun. I learned a lot. I'm looking forward to listening to it again.
Thank you for your patience, and I tried my best, but I hope it's entertaining for your listeners.
Hold on, geeslings. Before you go, please like, subscribe, follow if you haven't already. Smash all those buttons. And also, if you haven't followed me on Twitter at Robinson Earhart, or if you're not joining me every morning as I eat my pint of ice cream on Twitch at Robinson Earhart on Robinson Eats, please do so.